Well, here we go. We're going to do a two-sided test. This test has to do with this data that was collected in midge traps. Midge are these little flying insects that are along the river around here. And they trap midges to determine changes in midge population on the river, these bugs that the fish eat. I guess the fish eat the larval form, but they trap the flying ones to see how many midges are around. So here's some midge trap data. 30 different traps were they left out for 24 hours, and that's how many midges they caught. 11, 15, 8, 14, 15, 6, and so on. We're looking for evidence of a change in mu. Mu would be the long-term mean number of midges caught in the traps along the river. Historical data says that mu tends to be around 12.57. Okay. So we're looking to see whether or not the values we see there are significantly different in a statistical sense from reflecting a mean of 12.57. So could those have come from a normal distribution whose mean was 12.57? And we're using as our alternative, we're just looking for a change. More midges or less midges would be equally interesting to us as scientists. So the alternative is not equal to. Is anything happening along the river? Are we losing midges, gaining midges? Is there some kind of environmental impact from something that we've done? Whatever. So there's the test null and alternative hypothesis we're going to use. And up here we got the test statistic. So in the test statistic you put the null hypothesis mean here. So if that's the wrong mean, you get crazy answers for a t, and t looks something like z. And then we put what, the values are something like what z, so something like bigger than 2 or smaller than -2, you start to get concerned that maybe there's been a change. We compute x bar for our data, we got 14.2, we got s. It says sx on the calculator, so that's what I got. And then when you put all that information into t, you get 1.95. So those are the first steps. No matter how you're going to analyze the experiment, whether you're using the p-value approach or the classical approach, you're going to compute t. And we did so. Here we go. So now we're in the analysis section. That's just the boilerplate you have to do section. Following the classical approach, so the classical approach identifies a critical value for t that your statistic has to beat in order to reject the null hypothesis. Okay. We're setting alpha equals 0.05 because that's typically what we do. The degrees of freedom here, degrees of freedom is n minus 1. That's 30 minus 1. That's 29. Why do we care? Because the tables list degrees of freedom, not sample size, along the border. And then we're going to look for a tail probability. So what's the story here? It's a two-sided test. And so we reject if t is too big or too small. And the total area here is supposed to be 0.05. And so we're going to look up a tail probability of t of 0.025 in the tables. And so I'm going to try that again to make sure I did it right. Degrees of freedom 29. I'm there on 29. Sliding across to 0.25. 2.045. It's correct. Okay, 2.045 like that. So the story is I need a t bigger than 2.045 or smaller than negative. So I'll put that here. 2.045. So this is 0.025 on each side. And down here, minus 2.045 nt. So one thing that students do, they look it up in the z tables, not remembering that we're using t. So be careful about that. And then we look for our conclusions. Did our test statistic beat this value? Well, here's our recorded value is really close. Observed value was 1.9549. Not quite big enough. So our conclusions are failed to reject you say, but it was close. So lots of times when we have a test statistic that's pretty close to the rejection level, we might say The evidence was not statistically significant. True enough, not statistically significant, but indicates further study might be needed. Okay. The sample mean was too close to 12.57 to cause us to reject agent. So in more context, we can't say that the current data indicates the mean has changed. Current data can't I say current data doesn't support a conclusion that mu is not equal to 12.57. Try to say it every way I can. So that's the classical approach. Identify a critical value, see if you beat it. If you don't beat it, fail to reject. We did it. We failed to reject, but it was close, and so we would make a comment about that in our conclusions. So that would say there might have been a change, but it was too small for our procedure to detect. It could have been because the sample size was only 30, and the change wasn't very big, because here's the X bar of 14.2. It is bigger than 12.57, but there's a lot of variability present. There's a standard deviation, so it didn't come out to be the equivalent of very many standard deviations, so not quite large enough. It'd be too easy to get that type of t-value just randomly for us to say that when we computed t, that number's not right. That's the idea. So this can easily happen with random variation, and so we can't reject the null hypothesis. All right. Now we're going to move on to the p-value approach.